Do, 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 do. Is this the right microphone? I think this is the right microphone. Okay. Hello, how's it going? I'm not done grading exam 2, but I'm going to start lecturing anyway. Hey, I sent this puzzle to the group text after the exam. Did you solve the puzzle? Did you solve it? I love this stupid puzzle. It's a maze, but it's not really a maze because you have to move in the direction that the boba is facing. So to start here, you must go this way, and this way, and this way, and then you go to over here, and down, over, up, over. And the goal is you get to add one downward-facing boba to reach the goal. If you haven't thought about the puzzle, think about it, because this is a good puzzle. This is like, I love this puzzle. Pause it and think. Did you think? Here's how it goes. Boba, boba, boba. Over here. Down here. Over here. Up here. Over here. Up here. Over here. Down here. Over here. Down here. Over here. Up here. Over here. Down here. And now it's time to add our extra boba. Our extra downward facing boba goes here. Why does that work? Because if we go here, and then we go down, look where we land. We land over here. Who tells us to go over here? Who tells us to go up here? It's a total cheaty outside the box thing, but it's totally not cheating at all, because look at this guy and look at this guy. They are definitely facing to the right and up. And they are definitely the same thing as the other ones. I love this kind of outside the box thing when it doesn't feel like it's a cheat. Oh, this is like a totally literal outside the box thinking type of thing. What are we up to? Exam 2, the one we're starting to get ready for. So exam 1 was all about integrals. You had to learn how to do a bunch of integrals. Not much of that stuff is going to be useful for the rest of the year, so if you bomb that first exam, I guess good news, you don't need that stuff to get on with the rest of the class. We're talking about sequences and series. Our ultimate goal is to understand what an infinite series is, and to determine when it converges, at least much of the time. Before we talk about a series, we talk about a sequence. And I guess we'll make a big deal later when we say what a series is, but a sequence and a series in English are usually like synonyms, and in math they are not synonyms. They mean very different things. A sequence is like a list. A sequence is basically an infinitely long list of, for us, usually real numbers. They don't have to be numbers, they can be any mathematical objects. What does it mean to be a list? It's a function. It's a function that maps n, or maybe n plus, or another subset of n, into R. Do you know these symbols? Math bold. Okay, do I talk about this? There's these useful mathematical notations for worlds of numbers. N is the natural numbers. Some people disagree about whether 0 is a natural number. In most math contexts, 0 is always counts as a natural number. The main reason you would want to separate it, to me, it's easier to make it because you can write n plus to mean positive naturals, which is that but without 0. So like these are the numbers that the ancients knew. If you wanted to talk about numbers in Mesopotamia, you were probably talking about whole numbers. At some point someone figured out fractions. I know the Egyptians had this. It's sort of unclear where the origin is. This is the set of all fractions of whole numbers. Oh, I guess before that we have z is the integers, which is the naturals and the negative naturals. So it goes both directions. Q is the set of rationals. So it's the set of all fractions, 2/3, 1/2. 0 counts as 1 because I can write it as 0 over 1. A whole number counts as 1 because I can write it as itself over 1. Pi is not 1, even though I can write it as pi over 1 because pi is not a whole number. The fractions have to be integers. Math bold R is the real numbers. C is the complex plane. The set of all A plus BI. You can go to math bold H is the Hamiltonian. Ring is where you have an I and a J and a K. There's all these things. In older textbooks from like the 20s and 30s, the natural numbers would be written as a bold N, was the standard math book notation for the natural numbers. And then it became customary that when you're trying to write a bold N on a chalkboard, like I just tried to, it's terrible. So instead of writing it with a bold, you write it with an extra vertical line in it. And now that's become Blackboard Bold is the name of this font of mathematicians trying to make a letter bold in a lazy way, is what this font is called. So it's a function from, this is Blackboard Bold N to Blackboard Bold R. It's a function who's defined on the integers, whose outputs, for us, they could not be reals, but for it, they will be real valued. A sequence you don't usually write in function notation. You could say f of 1 is 2 and f of 3 is root 5 if you're talking about a sequence. But instead, we write it as a sub 1 is 2, and a sub 3 is root 5, and etc. Functions, we are most likely to grab the letters f, g, h for our first few functions that we're using as examples. Sequences, we're more likely to use the letters a, b, c as our basic default letters for sequences. And we indicate the third thing in our sequence by a subscript 3. It's usually defined on the natural numbers, which would mean that a0 is defined. Sometimes a0 is not defined. It's in math, you sort of want to let it go either way, whether or not 0 is defined. A very common thing is you don't define what the 0th element of the sequence is, and then later you go back and say, well, if there was a 0th element, it would have been this, so maybe we let it equal that when it's appropriate to do that. Computer scientists get really worked up about whether their arrays start at a 0 or at a 1, and it makes a big difference. We don't have to think as hard about that. Because by and large, when we're talking about a sequence, we don't really care too much about the first few terms. We are more interested in the infinitely many terms after that. Let's just do some goofy notation with sequences. So for example, I can write the sequence n over n plus 1. Often I'll add a little index on the side that says when this is defined. So this is from n equals 1 to infinity. This is a way to write a sequence. Our formula here is given that an is defined to be n over n plus 1, and it's defined if n is greater than or equal to 1 is a whole number, as a positive integer, if it's in n plus. What is this sequence? This is the sequence. The first one is 1/2, and then 2/3, and then 3/4, and then 4/5, and then so on and so on, and Scooby-Dooby-Doo. This way of writing it, come on, pen. This way of writing it and this way of writing it are complete definitions. If I write it like this, then it's not really a complete definition because I haven't defined what the first term is. Or in particular, what's the first term's index? Is that a0 or a1? Very often a sequence will start with 0th term or the first term. You can talk about a sequence that doesn't start till the 6th term. Like, that is also formally a sequence. For us, if I write something like this, the first term will be A1 unless specified otherwise. But different people will do it differently. When you're writing sequences, you got to be very careful about this dot 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 symbol. This is a thing you should be skeptical of when you see it. Anytime you find yourself using a dot 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 in math, you should be aware that you're doing something the lazy way, and you should ask yourself, would I be able to explain this without the dot dot dot? Maybe it's clearer to use the dot dot dot, which is the time that it's the right time to use it, is when I trust that my audience understands what I'm talking about. But in general, if you're writing something with a dot dot dot, you should have in your head, can I write this without that dot dot dot? Like if I write 1, 2, 4, 8, everybody's with me so far until I write 96.17 pi squared over 6, 11 to the 2/3, dot dot dot. The dot 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 is being indicated as if there's some pattern going on. What is this pattern going on? Nobody knows. Maybe you know. I don't have some secret code here. And you need to understand that when someone doesn't understand what you are talking about, your dot 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 is just as crazy as this. So when I'm writing something like this with a dot dot dot, I've got in mind, have I written the full explanation somewhere else on this page? If I haven't, could I have? If someone challenges me on this, am I prepared to fill in the blanks in a really specific way? That's a thing you gotta be careful for. Sequences can be defined in most of the ways a function can. You can do it with a formula. Oh, here's a good example. Let's find a formula for this sequence. 3/5, -4 over 25, 5 over 125, -6 over 625, dot dot dot. Can we understand what's going on? The numerators, if I ignore the minus signs, they are 3, 4, 5, 6. I get the pattern there. My denominators are 5, 25, 125, 625. I get the pattern there. They're multiplying by 5 every step. Note that when I did this, I didn't reduce this fraction. Reducing that fraction just makes the pattern less obvious to a person trying to get what's going on. So very often in these situations, it's way better to not simplify something, even though it obviously does. Can I come up with a formula? Remember, this is supposed to be the n equals 1 term here, and this is supposed to be n equals 2. And this is supposed to be n equals 3. What's going on in the denominator? The denominator looks to be 5 to the n, right? That's 5 to the 1, that's 5 to the 2, that's 5 to the 3. Cool. The numerator, ignoring the minus signs for a second, 1 maps to 3, 2 maps to 4, 3 maps to 5, so that's n plus 1 that's on top. And then what do I do with the minus signs? There are many examples of sequences that alternate positive, negative, and it's common enough that you want to be ready to write down -1 to the n when the time comes that you need it. -1 to the n is a sequence that's, when you plug in n equals 1, you get -1. When you plug in n equals 2, you get 1. n equals 3, you get -1. n equals 4, you get 1. Wait a minute, that's not what we wanted. That's the opposite of what we wanted. That's negative, positive, negative, positive. This sequence is supposed to be positive, negative, positive, negative. There's a couple ways to write that. I can put an extra minus sign out here to fix that. It's way more clear what I'm doing, though, if I write that as -1 to the n plus 1. Or -1 to the n minus 1 does the same thing. This is probably the most straightforward way for people to understand what this sequence is. So for functions, we almost only talk about functions we can write down a formula for. For sequences, we're more likely to come up with sequences where it's not clear. Like, here's a sequence: 3, 1, 4, 1, 5, where these are the digits of pi. So what's a formula for this? AN equals, I don't know, it's really hard to come up with a formula that gives out the digits of pi. This is not a clear thing to do. I guess a cheaty way to do it is to take pi, multiply it by 10 to the n, take the floor of that, take that mod 10. There's like ways of doing that are terrible, and you don't want to have to do them that way. Like, this doesn't really get to the point of it, which is come up with a formula that spits out digits of pi. This is rough. There's other sequences that are where you can give a formula, but it's less formula-y than a traditional formula. If I say, here's a sequence. Have you guys heard of the Fibonacci sequence? When I was in elementary school and middle school, we were constantly talking about the Fibonacci sequence. 8, 13, 21, 34. The thing about the Fibonacci sequence is every term is the sum of the two terms below it. 2 plus 3 is 5. 3 plus 5 is 8. 8 plus 13 is 21. 13 plus 21 is 34. So whenever I've got the sequence, I can just write it for as long as you want. 55. 89. 130. 144. 3 carry a 1, 8 and 15 is 233, so on and so on. How would I come up with a formula for that? This is going to be an example of a recursively defined sequence. I can tell you how to find the nth term, but you need to know what the terms before it are. The terms would be an is take the term before it and add on to that the term before that. So an minus 1 is the symbol for the thing for n minus 1. N minus 2 is the symbol, is how you write the term, two terms before an. Adding those gives you an. But this only works if n is greater than or equal to 3. I can't use that formula for n equals 1 and n equals 2. So part of my recursively defined sequence is I need to give you the first starting little bit. So we also need to give you that a1 and a2 are defined to be 1. So now I've said how to define a1, I've told you how to define a2, and I've told you how to figure it out for anything bigger than 2. We can see from the fact that we started writing down terms of the sequence that this formula is all you need to define the thing. It feels like an illegal thing to do, like you shouldn't be... it feels like a... what's the word? A circular definition. If I'm asking you to define a word I don't know, and your definition uses that word I don't know, then that is supposed to be a bad definition, right? Well, part of the problem is, well, in life, a dictionary is entirely made out of words. A dictionary can't define what the words mean without using words. In math, you can do a little better than that. In math, you can talk about building from the ground up, more words and then more words and then more words. But that's not what's going on here. What's going on here is that a recursively defined sequence works in part because of the fact that a sequence is one at a time, one at a time, one at a time. Only defining the next thing in terms of the things before it works for a sequence in a way that it wouldn't for a function. If I wanted to do the same thing for a function where f of x is f of x minus 1 plus f of x minus 2, the function goes forever to the left, and it doesn't just have points on it, it has all these fractional points on it. You would need a lot more information than just what are these starting two things. For a sequence whose terms only exist one at a time in a row, you don't need to worry about that. Can you come up with a formula for this? If you take a discrete math class, you probably will. You can. It's a linear combination of exponential functions. But that definition is way worse than this one. Okay, so that's what a sequence is, and those are the terms we use. Those are some of the notations we use when we're talking about a sequence. Let's get into some of the big ones. Definition. We say a sequence has a limit I will often write a sequence with curly braces. We say a sequence from n equals 1 to infinity has a limit. L, and write limit as n goes to infinity, a sub n equals L, if it's the same epsilon delta type of thing you were doing in Cal 1 with a sequency twist on it. For every epsilon greater than 0, there exists not a delta. The thing we want to say is that the sequence will eventually be very close to L. How close? Well, we'll say for any epsilon, it will eventually be within epsilon of L. How do I know that how do I define that word eventually? We say there exists a capital N, capital to indicate that it's big, an integer, so that whenever little n is bigger than big N, an minus L is smaller than epsilon. Traditionally, they put a strictly less than, although it doesn't make a difference. This works exactly like the epsilon delta stuff. I'm not going to make you work with the epsilon delta definition that much, although I think I'm going to do an example with it soon enough. And by and large, the stuff you do with computing limits is exactly the same. If I say that the limit, if I wanted to work out the limit as n goes to infinity of n over n plus 1, a trick you should have learned in Cal 1 is multiply the top and bottom by 1 over whatever the biggest power on bottom is. I have a power of n to the 1 on bottom. I multiply the top and bottom by 1 over n. I get 1 over 1 plus 1 over n. I want to say I know that 1 over n goes to 0, which means that I know that this is going to go to 1 over 1 plus 0 equals 1. And that is true, and that works. Why am I actually allowed to do that? I'd like to just lean on the things I know for functions to tell me that that works. Why does that work? Well, here's a nice theorem that lets us turn any sequence question into a function question. If I have a sequence that agrees with a function, so that an equals f of n for all, maybe all sufficiently large, n, and if the function has a limit, then the sequence has a limit. Many sequences, because they come from simple formulas, they are intimately connected with a function. And our ability to do calculus on that function, for example, I can do L'Hopital's rule on a function. That's a thing that I can't do on a sequence. I can't talk about the derivative of a sequence, or the derivative of the numerator, or any of that junk. Doesn't make sense for sequences, but does for functions. If your sequence agrees with a function, you can still use L'Hopital's rule on that function, and that'll tell you, because my function is very close to L, an must also be very close to L. We started using some phrasing in this theorem. The sufficiently large. The key thing going on here is that for a sequence, when I'm asking about the sequence to have a limit, I don't care about the first 10 terms. I don't care about the first 100 terms. I don't care about the first million terms. You can mess around with the first million terms of my sequence all you want. You're not changing what the limit is. Why? Because the limit is what happens in the long run. It's what happens after the first 100,000 million terms. So messing around with the first part doesn't matter. So when I'm saying that if my sequence behaves in a certain way, then I'm making conclusions about the limit. I don't really care if it behaves this certain way for the first part, and this can be very convenient. There will often be situations where my sequence does the thing I want it to do eventually, and being able to say for all sufficiently large n that saying it's after a certain point this thing is going to be true is a nice handy piece of phrasing that lets us get around little annoying, oh, that's not actually technically true. Well, it's eventually true. This is a nice thing to be able to say. Cool. That's the definition, or that's our fact that a sequence can be distilled down to a function sometimes. Here's a definition. We say that the limit can be infinite. The same way we say a function can have an infinite limit. How do I know that the limit is infinity? I want to be able to say you become within epsilon of infinity, but nothing is within epsilon of infinity. What's the right version of saying that? Instead of saying being close to infinity, you just say it's big. Instead of saying for any epsilon that is closeness, we say for any big number. I'm writing capital M because I'm imagining that this is big, although if M is small, that's even easier. For any positive number M, there is a positive number N, so that if little n is bigger than big N, so if you are past this starting point, then AN is bigger than M. Past a certain point, the sequence will be very big. How big? However big you want. Although if you want it to be even bigger, you might have to wait a little longer for that certain point when it starts being true. This works essentially the same as it did for a function, except we're only plugging in integers. When I say if n is bigger than n, it has built into it that n is an integer. This is the nice thing about switching letters, is I can ask you about n squared, and I don't need to have told you that n was a whole number. It is very convenient to have built into us that x and y are going to be real numbers. M and n are going to be integers. Z, if you ever get to a complex analysis class, is going to be the typical first variable you grab for a complex number. Sometimes you use a special font for a type of thing. Right, and this is just convenience. There's not a mathematical fact that lowercase n always indicates a whole number. You can let lowercase n be pi squared over 6. It's just weird if you do. There's probably times where the context for it makes sense, though. Oh, and we only defined it for positive infinity, similar for a limit of negative infinity. Here's a theorem. Modern textbooks call this the squeeze theorem, which bums me out because when I was an undergrad, the textbooks all called it a sandwich theorem, which is a much cooler name. I wonder, there's a fairly recent theorem called the ham sandwich theorem that I wonder if that's the reason that this thing lost its name. The sandwich theorem says that if you have a sequence that's sandwiched between two other sequences, or a function that is sandwiched between two other functions, then the limit must be the same. Oh, that's right, you should have seen this in Cal 2. This is how you prove that sine x over x goes to 1 at 0. Well, it's the same thing for sequences. If you have sequences with an less than or equal to bn less than or equal to cn, and I don't actually need that it's always true, it's enough that it's true for sufficiently large n. let's see, if this holds, if this inequality holds for all, not necessarily all, but maybe just all sufficiently large, n, and if the big function and the little function both have the same limit, then the middle function, which is stuck between them, also has the same limit. If you're bigger than something that gets very close to L, and if you're less than something that gets close to L, then you must be close to L, is the conclusion here. Let's try using some of these. Let's compute the limit as n goes to infinity, natural log n over n. How would I do this? Just glancing at that thing, I'd like to use L'Hopital's rule. How do I do that? To me, the shortest number of letters needed to do that is to say, well, let's just take... I can't use L'Hopital's rule on this, because you're not allowed to take the derivative of a sequence. Natural log n doesn't have a derivative. I can take the limit of natural log x over x using L'Hopital's rule, and I've got a fact from 2 pages ago that says the limit of the sequence will equal the limit of the function. But I need to be good and show that I'm making the conversion from the sequence to the function. And I don't need to write out a bunch of sentences about that, just writing this is enough. It might be better to say let f of x be natural log x over x. Then f of n equals ln n over n. And we can take the limit of natural log x over x equals, according to L'Hopital's rule, infinity over infinity case, it's 1 over x over 1. The limit of 1 over x is 0. I should mention that I'm using L'Hopital's rule. Infinity over infinity case. So the limit of natural log n over n is 0 as well. You need to start getting into the habit of being able to express yourself in sentences rather just in lines of math, right? This is the place we're headed to by the time we get to exam 2. Exam 2 you will mostly be answering in paragraphs and not in equations. Or maybe it's more like half and half. There's an example of computing a limit by converting a sequence to a function. Cool. Actually, let me turn on some music. If I never turn on music, I kind of go nuts during these lectures. Let me skip the ad. There's my notes. Cool. Here's another example. Let's compute the limit as n goes to infinity of negative 1 to the n over n. Can I imagine this sequence? When I plug in n equals 1, I get negative 1 over 1. When I plug in n equals 2, I get positive 1/2, negative 1/3, positive 1/4, negative 1/5, so on and so on. This doesn't seem very well suited to the function theorem. If I tried to write f of x equals negative 1 to the x over x, this negative 1 to the x is very poorly behaved. What do you get when you plug in a half? Are you going to let it equal I? What do you get when you plug in 3/4? Like, this is a very bad function. So the obvious way of converting our sequence into a function leads to something that I don't really want to try and talk about a limit of, right? You could probably try, and the limit would probably still be the correct thing. Looking at the sequence, I can see that the terms get closer to 0. How would I prove that? How can I make sentences that justify this thing? The hardest thing in math is converting, or saying this is the hardest thing feels misleading. There's actual hard stuff in math too. But a very hard skill that you're going to try to have to learn this semester is taking a thing that is so obviously true and figuring out what are the 3 sentences that make it even more obviously true that I've actually justified it. Like, look at those terms. They get close to 0, right? Okay, I need to be able to convince somebody of that. Like, I need to be able to break that down. How do I know it's getting close to 0? Do I need to use an epsilon? I probably could go as far as using an epsilon type thing. We're going to get around it by using the squeeze theorem. Negative 1 to the n is either negative 1 or 1, right? Which means no matter what, it's between negative 1 and 1. So, negative 1 over n is definitely less than or equal to negative 1 to the n over n is less than or equal to 1 over n. And we have that the limit as n goes to infinity of negative 1 over n is 0, and the limit of positive 1 over n is 0. So, by the squeeze theorem, our sequence, which is stuck in between those sequences, the limit of negative 1 to the n over n is 0 as well. Period. Done. Paragraphs. I'm going to take a sentence. I'm going to try and remember to stop for a minute and say what's good and bad about these paragraphs. One thing that I've done is pretty bad is I've made a sentence that is just math. When you write a sentence, the rules of English are that you should start with a capital letter, and you can't just capitalize things in math. In particular, you can't capitalize a negative 1. So this is kind of bad form for math writing. When you write mathematical writing, you don't start with a number. You always come up with an excuse. Like, this is what this word so is doing here, is it's giving me something to put the capital letter on. What would I do to get around this? A typical starting thing is, you might say, we have this fact, so this fact, and therefore this fact. Another thing you want to do in math is you want to avoid using, I guess this isn't a math thing, this is an English thing. You want to avoid using the same word all the time, every time. So mathematicians have come up with a million different words for therefore. So this, therefore this, hence this. From that we derive this, which leads to this. You want to mix up your language just to make it not make you fall asleep while you're reading it. Let me show you something real quick. I'm a mathematician. I write math, try and publish papers. Teaching, Andy Tech. What's a paper I've got? Let's grab something from 2012. Here's a finitely ergodic. Yeah, what's this going to be? Oh. I've been working on this one for forever. Here's a draft from June 2019. Show me the output. Do you work? Hey! Math by me. Is there any place where I have a bunch of mathy stuff going on? Show me a display with a bunch of... I know I have some crazy inequalities and junk later. So, like, look at this. This sentence starts with a capital letter C. Consider the graph G with the sets in P as vertices, which gives the edge this to this. Weight equal to this display. Every mathematical equation in a math paper is always incorporated as part of a sentence. With weight equal to blah. Look at this. I got a period at the end of the sentence. This is what you do. This expression, blah, is incorporated as a noun phrase into this sentence. With weight equal to this mess. I'm still in the middle of speaking, so I still have this sequence. There's no equation here. This is not an equal sign. This is all just a number, this number minus this number. Compare that with the next paragraph where... that one's not a good example. Here's one where I have an equation. We have blank equals blank. Now my thing is not a noun phrase, it's an independent clause. We have statement. The same way you would say, we learned that the dog is brown. You wouldn't say we learned that the dog. You don't just put a noun here. You treat an equation like it's an independent clause with a period at the end. You treat something that doesn't have an equal sign in it as a noun phrase, as a noun possibly with a bunch of adjectives and prepositional phrases attached to it, but something that is in the category of noun. Sentences end with periods and they start with capital letters. Blah, blah, blah. Do I have a good example of me finding an excuse to start a sentence with... Yeah, here we're letting H be one of these things. I'm using the word fix to say I have a word before there to start my sentence. Mathematical writing has these inequalities in them as phrases in them. They are treated like, I believe the word is an independent clause for any chunk of a sentence that could be a sentence on its own. Here, I guess they're less independent because the thing I'm telling you is you shouldn't try to write that on a sentence on its own. You should put some words before and after it to build a sentence around it. But, yeah. Okay. I should clarify the converse. We did a lot of talking about that if your sequence matches a function, and if the function has a limit, then the sequence also has that limit. The converse isn't necessarily the case. Consider the limit as x goes to infinity of sine pi x. How would you take that limit? What does sine pi x look like? I know what a sine wave looks like. This is going to look like a sine wave, but you've done some kind of scaling factor of pi here. What is the limit of this? It's not going to have a limit. It's going to go up as high as 1. It's going to go down as low as -1, over and over and over and over. So the limit doesn't exist. Well, now let's consider the limit of the same sequence. What's the limit of sine pi n? Now the limit does exist. Because now I need to think about what do I get when I plug in 1. Sine pi is 0. Sine 2 pi is also 0. Sine 3 pi is also 0. Sine 4 pi is also 0. When we scaled it by pi, we rigged it up so that every time we plugged in a whole number, we would get 0. Since sine pi n equals 0 for any integer n, we have the limit as n goes to infinity sine pi n equals the limit as n goes to infinity. We just said that thing equals 0. The limit of 0 equals 0. Done. I came up with a sentence to justify my conclusion. So this is a goofy example of how, like, because the function does more things than the sequence does, it can behave badly. It can go up to 1 and down to -1, even though at the whole numbers it's doing the exact same thing every time. And any sequence that has a limit, you can add on a sine pi x. You can multiply this by an x squared or something. It still equals 0 at every integer. Throwing on the x squared now makes it even bigger. Like, whoa, what's going on? It's annoying, but it is what it is. While I'm talking about sine pi n, might also mention cosine pi n. Come on, where's my mouse? Cosine n pi or pi n? I'm not sure which way is the more normal way to write it. I would want to put a pi before an x, but I'm not sure what I want to put first when it's an n. There's a weird... It's really hard to get your handle around. I heard a thing about adjectives in English that any English speaker has memorized the order that you need to put adjectives in. Like, if I talk about an expensive little pink car, I would never talk about a pink little expensive car. That sounds weird to any native English speaker, but like nobody could list what is the order you put them in. If you're learning English, you memorize the order, and there's like 8 different things that have to go in this order, or it sounds weird. There's stuff like that in math about you want to put the simple part first. You want to talk about x squared log x. If you write log x squared, that looks weird. Anyway, I'm rambling. What is cosine n pi? If I think about what I get, cosine of 0 is 1. Cosine of 1 pi is cosine pi is negative 1. Cosine 2 pi is 1 again, and so on. Cosine n pi turns out to equal negative 1 to the n, right? 0 is 1, 1 is negative 1, yeah. So a couple pages ago when I talked about how negative 1 to the n over n is not something that you can naturally convert into a function, writing negative 1 to the x over x is bad because negative 1 to the x is very badly behaved. You can kind of get around that by replacing any negative 1 to the n with a cosine of n pi. And now cosine x pi is well behaved. But again, L'Hopital's rule is not a really good choice there. I think L'Hopital's rule on cosine, is it? I'm not sure what happens if you try and use L'Hopital's rule there, but I don't think it's a great idea. Okay, back to definitions. The sequence is increasing, I guess I should say the sequence AN. It's increasing when AN plus 1 is greater than or equal to AN for all n. Or what for all natural numbers n, or whatever the domain is. The next term has to always be bigger than the current term to be increasing. And we say greater than or equal to. Why don't I say greater than? Some people will say, well, let me finish this definition first. The thing we say for greater than is we call that strictly increasing. If AN plus 1 is bigger than AN. This notation is not standard. I've taken math classes where people will say AN is non-decreasing. When AN plus 1 is greater than or equal to AN. It doesn't necessarily increase, it might stay the same, but it definitely doesn't decrease, and is increasing when you have strict inequality. Again, for all n. All of these are for all n. And in each case, it's for all n in whatever the correct domain is. Notice that this definition of increasing is not the same as this definition of increasing. And that sucks. The good news is that by and large, the difference doesn't matter. There are very few places where a sequence is most of the time increasing, but every once in a while it stays the same. Like, that doesn't happen naturally for, like, if that happens, it's weird and interesting that happens, right? It's also good news because most of the time we don't actually care. When I'm telling you that when I need to know that something is increasing, I don't really care if it ever equals the same, right? By and large, any statement that's going to be true about an increasing sequence will also be true for a strictly increasing sequence and vice versa. So most of the time we don't really care about the differences between increasing and strictly increasing, but we're going to use these words because most of the time this is the version of the word that we're going to use most of the time, so we'd like that to be the simple word. I don't often need something to be strictly increasing, so I'm just going to use the word increasing to be the one that we use more often. Yeah, the main times that you really care about strictly increasing are because you're doing something with the differences of terms. And sometimes when you're talking about things, you need them not to be zero. Maybe we're going to divide by that or something. So that's a reason you might actually care about the difference. I don't know why that would very often be the case, but sometimes it is. And strictly increasing is sort of a nice way to, after the fact, say, oh, by increasing, I meant for this to count also. I didn't say it was strictly increasing, I just said it was increasing. How dare you interpret the word increasing to mean actually increasing? Similarly for decreasing. I'm not going to rewrite all the definitions, but it's decreasing and strictly decreasing. Or the alternate definition would be non-increasing. We're not going to use these in this class, but if there's ever a situation where you really want to say increasing and emphasize that they're allowed to be equal, you can pull out the word non-decreasing and everyone will know what you mean. Like, it's nice to have the words non-decreasing and strictly increasing, where you definitely know what I'm meaning, as opposed to increasing. I'm not quite sure what you mean, but probably the difference doesn't really matter most of the time in most contexts. But for us, when I say the word increasing, that's what I mean. A sequence is monotone or strictly monotone when it is either an increasing sequence or a decreasing sequence. And strict means we're strict. There's many things that are true about increasing sequences that are also true about decreasing sequences. Monotone is the word for increasing or decreasing. But increasing or decreasing about the whole sequence. You can't say this sequence always either increases or decreases because that's every sequence. What I mean is it's either always increasing or it's always decreasing. Either of those cases counts as monotone. It's worth noting that all of these you can stick the word eventually. The sequence is eventually increasing. If there is some big N, so that an plus 1 is bigger than an, or equal to big An, whenever n is bigger than big N. The first some big number of terms might not be increasing, but after that point it will be increasing. Most of the time, we care about the long-term behavior of a sequence. For us in calculus, the interesting part of a sequence is the infinite part at the end. A list of finitely many numbers we don't take limits of, we don't ask these complicated questions about. It's the infinite part that we care about, so most of the time, something that's eventually increasing will do exactly what we want it to do also. Right. Let's talk about bounds. A sequence is bounded above when I was in undergrad, this word made more sense to me if I thought of it as bounded from above. Although I don't think people actually say it that way. This is just the way I had it stuck in my head to remember what it meant. It's bounded above if there's a real number n. I should name the sequence an. So that an is less than or equal to m for all n. In this case, we say the number m is an upper bound of the sequence. It'll be tempting to say that talk about a sequence being eventually bounded above, but you immediately, on a little thought, realize you never really need to say the word eventually, because eventually means maybe the first bunch of terms aren't bounded above. Well, any finite list of numbers is always bounded above. If you hand me finitely many numbers, the biggest one is an upper bound. So those first finitely many were already bounded above. The thing I'm worried about is maybe the list of numbers gets bigger and bigger to infinity. The word bounded above is already talking about eventually. You might want to talk about whether m is a bound for all sufficiently large numbers, but by and large, we don't really care about. If you have a bigger bound, nobody cares. It's still bounded. And similarly for bounded below. You're bounded below if an is always going to be bigger than m for some m. Okay. We've defined the words bound. Oh, a sequence is bounded. Do we care about that word? If someone just says bounded, then it's bounded above and below. I should make this better. If it's bounded above and below. We can say that it's bounded. That is, there is some m so that the absolute value of an is less than m for all n. There's something so that even in absolute value, it's not as big as m. The opposite of it is less than m, and it is less than m, so it's both m is an upper bound and negative m is a lower bound. And in these m, we imagine capital letters in these conversations being some really big number. Like when we put a capital letter, I'm saying there's some very, very big number m. Maybe the number m is not that big, but it will also be true for big numbers. Okay, the thing we want to say, this is a theorem, or maybe it's an axiom. That a bounded monotone sequence has a limit. Is this fact obvious? So, for example, consider, I guess this is not, my nose is itching. Hang on, let me blow my nose real quick. Okay. So consider this fact. Consider the fact that, consider an increasing sequence that has an upper bound. So I have A1 is less than A2 is less than or equal to A3, less than or equal to A4. And these numbers are getting bigger and bigger, on and on. Are they going to infinity? Well, if they have an upper bound, I'm saying they're all less than or equal to some number m that is an upper bound. So they're increasing, but they stay less than m, they can't increase to infinity. Is it obvious now that there's a limit? It is not obvious that there's a limit. A question you can ask is, what is the least upper bound? There are many upper bounds. If m is an upper bound, then any bigger number will also be an upper bound. So like any sufficiently big number is an upper bound. We can ask, what's the least upper bound? Does it exist? Well, the definition of an upper bound was you're allowed to be equal. If I think about all the upper bounds, I can think about a decreasing sequence of here's an upper bound. Is it the least one? No, here's a lesser one. Is that the least one? No, here's a lesser one. Just keep shrinking it down. Any smaller number, yeah. The least upper bound, it turns out it does. Once I know that it exists, it's the limit. How do I know it's the limit? Well, once I have an upper bound, I'll call it LUB for least upper bound. My sequence is increasing. How do I know that the least upper bound is a limit? Well, the definition of limit is that eventually all those terms are going to be within epsilon of it. Think about some epsilon window for some small epsilon. Do I know that the terms are eventually all going to be within epsilon of it? Well, the sequence is increasing, and it's not passing my least upper bound. If it ever gets within epsilon, then all the following terms will be within epsilon. Do I know that the terms will eventually get within epsilon? Well, if they didn't, then my least upper bound minus epsilon would be an even lesser upper bound. So if there is a least upper bound, then by definition, it must be the limit. Or not by definition, but by this little piece of reasoning, that since that number minus epsilon is not an upper bound, because it's the least one, the terms will get within epsilon at least once, and then they will stay there forever, because it's an upper bound. So there's a proof that the limit exists if I know there is a least upper bound. How do I know there's a least upper bound? I said this theorem might be an axiom. When you get to real grown-up mathematics, the real grown-up mathematics is the pursuit of theorems. A theorem is, you can think of it as being like the word fact. It is a true statement. But a theorem isn't just a true statement. It's a true statement that has a mathematical proof for it. Grown-up math is not about computations. It's about writing out proofs. It's about discovering a proof that this thing must be true, or a proof that this thing must not be true, or, whatever. And the way you prove things, you can break this down into rigorous logic if you take a logic class that goes into symbolic logic and predicate quantifiers and junk like that. is you need to start with here are some base statements that you know are true and use those to generate new true statements. And the fact that least upper bounds exist is one of the fundamental axioms about the real numbers. Here's a fact that there's a story that in ancient times, Pythagoras, okay, this part is probably true, that Pythagoras ran a cult, and he had a cult that was obsessed with rational numbers. Pythagoras had learned how to add fractions. He probably learned it from the Egyptians, who knew it way before him. And, like, he thought this is great. This solves math. Like, you can think about how if you know the whole numbers, and the fact that there's these big gaps between them is like a big mystery. Like, there's huge chunks of space that are just missing from your mathematics. But you learn about fractions, and you learn about, I don't know, 22 over 7, and you learn about, like, you learn how to add fractions, and it's a big deal that, hey, not only your number line is now full, like, all the spaces have been completely filled up. Okay, the version of the story that's probably not true is that apparently Pythagoras had a slave, and the slave figured out a proof that the square root of 2... He didn't use the notation square root 2. I think he was saying that they knew square root 2 was the diagonal of a right triangle. Like, they had the Pythagorean theorem, you might guess from the name. And, like, Pythagoras was sort of casually trying to figure out what is the fraction that when I square it will give me 2. And the slave came up with a proof that there is no square root of 2, that it can't be written as a fraction. And I can show you that proof right now. I don't know if this is his proof. But if p over q squared is true, is the fraction reduced? Reduce the fraction if it's not. Actually, I'm trying to talk about writing proofs. I should write out a good proof of this. Here's a theorem. There is no rational number. There are no integers, p and q, so that p over q is the square root of 2. Proof. Suppose there are. We're going to do what's called a proof by contradiction. I'm going to say that if there were such integers, then all of reality breaks down. I'm going to go from if those numbers exist, then something ridiculous must be true. That means that my hypothesis must have been wrong. Then we can reduce the fraction. P over Q. So if they have any common denominators, assume that we've cleared them beforehand. P and Q should not have any common factors. Then P over Q squared equals 2 says that P squared equals 2Q squared if I move the Q's to the other side. So P squared is even. Which means P is even. It's not hard to confirm that if you squared an odd number, you would get an odd number. So if P squared was even, then P must have been even. Okay, so we can write P is double something else. We'll call it 2R. Don't use the word so again, I just used the word so last time. I've already used the word so twice in a row. Let's use the word thus here. So P squared is even. Thus, we can write P is 2R. Since P squared equals 2Q squared, we find 2R squared equals 2Q squared. And that gives, I'm running out of all my therefores, 4R squared equals 2Q squared, and thus, and hence, 2R squared equals Q squared. So Q squared, and hence Q, is also even. But if P and Q are both even, then P over Q wasn't a reduced fraction. If it was a fraction, then it was impossible to reduce the fraction because the top and bottom of the fraction are always going to always be even, which isn't how fractions work. And the story is Pythagoras knew that wasn't how fractions work, and he figured out that his rational numbers aren't complete, so he murdered his slave, apparently. I think there's no actual evidence of this, but this is a story that shows up in math books as if it was true. Regardless of the weird backstory to it, it is a fact that if you lived in the rational numbers, as presumably Pythagoras did, it would not be the case that any monotone sequence has a limit. Why not? Because I could come up with a sequence that gets closer and closer to the square root of 2, but that number that is the limit does not exist in the rational numbers. If I lived in the rational numbers, there would be holes in the world that I wouldn't be able to see, which would mean that there are sequences for which there is no limit. Well, how do I know the real numbers are different from the rational numbers? The traditional way of defining the real numbers is you start with the rational numbers. You define a thing called a Dedekind cut. You define the rational number square root 2 by saying here's all the numbers less than square root 2. Here is all the numbers bigger than square root 2. That means there must be a number here called square root 2, which is the boundary between them. The definition is that least upper bounds do exist. And it turns out that once you add in those limits of sequences of rational numbers, then you end up in a place where the limits do exist, and like you don't need to. Now the real numbers are filled. You have filled in all the holes, at least in the terms of a limit. If you are mildly interested in math, there's a book called Surreal Numbers. The concept of a surreal number is due to John Conway, who's one of the great modern mathematicians. He actually died a couple weeks ago of coronavirus. It is a different way of constructing the real numbers than this traditional way, which is take the rational numbers and now cut these Dedekins and say that's what a number is. Instead of defining it that way, you can define it in a different way that leads to way more numbers existing. And if you lived in that real numbers, you wouldn't be able to tell the difference between those real numbers and these real numbers. It would also feel like you filled in all the holes and it's the onlyest natural thing to do. The surreal numbers include infinitely large integers. It includes the reciprocals of those infinitely large integers, which end up being infinitely small real numbers. And the weird thing is you kind of can't tell whether we're in that world or this world. Like, we sort of have baked into our intuition that there aren't any infinitely large integers, right? That shouldn't exist. But what's the definition of an infinitely large integer? It's something that's bigger than any other integer. And if those infinitely large integers exist, well, they aren't the case that it's bigger than every other integer, because it counts as one of the integers. Like, the things that are happening out there close to the infinity, we can't get our hands on, so we can't really tell what's out there. The difference between a world where infinitely large integers exist and where they don't exist is indistinguishable while you are living inside that world, if that idea makes sense. And it's sort of a weird, fundamental, hard to wrap your head around thing that it turns out we can't tell whether our model for the world allows for infinitely large integers or not. If our universe doesn't have infinitely large integers, you can construct a universe that excuse me. You can construct a universe that does have infinitely large integers, and it's just as consistent and sensible as ours, and you can't tell the difference when you're inside them. A good part about infinitely large integers, if we did let them exist, is that their reciprocals become infinitely small numbers, and we can sort of say, aha, that's what I meant by dx this whole time. That's an infinitely small number. That's sort of scapegoating the thing. That's sort of saying after the fact that makes sense. But it is a reasonable way to make calculus make sense. You can let You say our numbers are these. Now throw in some infinitely large integers. Those reciprocals, those are differentials. You can do calculus that way. It's not the normal way to do calculus, and we're not going to focus on it. But part of the reason that surreal numbers are so fun is there's a novel called Surreal Numbers that is a dialogue between two people who are figuring out the things that John Conway figured out, and it's a really good book about people figuring math out for the first time. If you want to know what it's like discovering math, this is a really good book for getting at that. I guess I say it's a really good novel. It's a really good novel in a really weird sense. If you want to read a novel by a mathematician, where the characters kind of don't exist and it's just about the math they're doing, and I think there's no descriptions of their places or their personalities. It's just them trying to talk through a difficult math problem. And they make mistakes, and they figure out what mistakes are caused. It's pretty cool. All right, let me get back to the point that I'm doing. I want to show you an example of a proof by induction. I'm not going to ask you to write a whole bunch of proofs by induction in this class, but it's a thing that you should have seen coming out of Cal 2, so I'm going to show you one. You get your money's worth in this class. I'm going to define the sequence. Consider the sequence, the recursively defined sequence. A1 equals 2, and AN equals 1/2 of AN minus 1 plus 6 if n is greater than 1. So the first term is 2, and the next term is always the previous term plus 6, half of that. So what's our sequence? A1 is 2. What's A2? A2 is half of 2 plus 6. 2 plus 6 is 8. Half of that is 4. What's A3? A3 is half of 4 plus 6. Half of 4 plus 6 is 10. Half of 10 is 5. What's A4? A4 is half of 5 plus 6. 5 plus 6 is 11. I get 11 over 2. That's the first time that it doesn't go. And dot, dot, dot. This dot, dot, dot makes sense because I did give you a formula for what's happening at every term. Here's our goal, is to prove this. Does this sequence have a limit? And the thing we're going to do is we're going to prove that it does have a limit because we're going to prove that it is monotone and it's bounded. This is a I can see 2, 4, 5, 5.5. It appears to be an increasing sequence, and it appears to be increasing slower and slower. So let's see if we can prove this. If I wanted to know that, so before I start trying writing my proof, what I want to show is that AN plus 1 is bigger than AN. How would I prove that? If I wanted to prove that, I would probably want to use the definition of AN, right? I guess it's AN plus 1 is the one that I need to expand. AN plus 1, since n has to be bigger than 1, since I'm already adding 1 to it, means 1/2 AN plus 6. Are you bigger than AN? How would I know that that's the case? I can solve this. That's AN plus 6 needs to be bigger than 2AN. If I subtract the AN, I need to know that AN is less than 6. Okay, as long as the terms are always less than 6, it will be the case that the new term is bigger than the last term. How would I prove that AN is less than 6? Maybe it turns out I need to prove that 6 is an upper bound, and then I'll know that it's an increasing. How can I show that AN is always less than 6? Well, what's my definition of it? I know that AN is 1/2 AN minus 1 plus 6. How do I know that that's less than 6? If I solve this, I need AN minus 1 plus 6 to be less than or equal to 12. So I need an minus 1 to be less than or equal to... Oh. What? To prove that an is less than 6, all I need to know is that an is less than 6. This feels bad. This feels like a recursive proof. I can't prove my statement assuming that my statement is true, right? If I can prove that an is less than 6, I just need to assume that I know that an is less than 6, then I haven't really proved anything, right? This is what this should feel like. Just like this feels like a bad definition. You shouldn't define your sequence in terms of what the sequence is. I shouldn't have to prove something assuming that the thing I'm trying to prove is true. That's not really a proof. Well, it turns out it is a proof. There's this idea called proof by induction. And it's one of the things that they expect you to have seen after Cal 2. And let's try this out. I'm not going to put this on the exam, by the way, but I think it does show up in the homework. Proof by induction. Here's the idea. If some statement S of n, this is a statement about a number n, if it's true for n equals 1, and if for any n, S of n implies S of n plus 1, then S of n is true for all positive n. All positive integers n. An analogy might be a dominoes. The idea is you've got these statements. Statement 1, Statement 2, Statement 3, Statement 4, Statement 5. I want to prove that they're all true. Well, the thing I'm doing with my proof by induction is I'm showing that if this is true, then this one is true. If Statement 3 falls over, that's going to knock over Statement 4. And if Statement 4 falls over, that's going to knock over Statement 5. And if Statement 5 falls over, that's going to prove Statement 6. So I've proved that the dominoes are in a line. That's called the inductive step. The base step is just knock over domino 1. And now you've knocked over every domino, or the dominoes have knocked them over for you. If it's true for 1, then it must be true for 2. And if it's true for 2, then it must be true for 3. And if it's true for 3, then it must be true for 4. And so on and so on. And that's what the integers are. You're tempted to explain when you do a proof by induction about this whole... since I did it for 1, and 1 goes to 2, and 2 goes to 3, that means I must have done everything. But when you're writing a proof by induction, you don't have to write that step. You say, I am doing a proof by induction, and whoever is reading it has been through Cal 2, they know what those words mean, that has baked into it. The thing we worked out was we wanted to show that our sequence was increasing, but to show it was increasing, we needed to show it was less than 6. To show it was less than 6, we needed to know it was less than 6 for the term before. This is exactly what we need for a proof by induction to happen. So, let's try writing this out. Let's restate our statements. Let an be the sequence. A1 is 2, and an equals half of an minus 1 plus 6 for n greater than 1. We will show the sequence as a limit. First, we show that an is less than or equal to 6 for all n. And we do this by induction. Actually, I'll use the classy sentence. When people write this, they say, we proceed by induction. For n equals 1, we have a1 equals 2 is less than or equal to 6. So the base case holds. For the inductive step, we want to say that if it's true for some n, then it is true for n plus 1. Now assume an is less than or equal to 6 for some n. It might be a good idea to switch letters here. Once you've gotten the hang of this, people usually don't do this, but for your first few times reading and writing about this, it might make more sense to switch to a different letter to say, now k is some specific number. Assume that it's true for k. We will show then that ak plus 1 is less than or equal to 6 also. This is called the inductive hypothesis, and this is called the inductive conclusion. We're saying that if you are true for some k, then you must be true for k plus 1. This is what the domino knocking over step is about. How do we show that? This holds since ak plus 1 is defined to be 1/2 ak plus 6. That's this formula when I plug in n equals k plus 1. This is less than or equal to 1/2 6 plus 6, which is 6. Why do I know this is less? Because I knew ak is less than or equal to 6. From that I got that ak plus 1 is less than or equal to 6. The inductive step works. And so ak is less than or equal to 6 for all k. I don't have to explain the rules of induction. My person reading this knows that I'm assuming something about k, and from that proving the same thing about k plus 1, and we did it, and we did the base case, so we got our claim. Next we show, maybe this should have all been one paragraph, that might have read better. Next we show ak is increasing. An is an increasing sequence. We already worked out on the last page that that's true if we show it's always less than 6. How do I know that? I wanted to show that an, let's see, what's the quickest way to do this? Here's where it's good to look at those notes. This was supposed to boil down to this. Let's see. an plus 1 is 1/2 an plus 6. This is, greater than or equal to. Yeah, since an is less than or equal to 6, I can conclude that 1/2 an plus 6 is less than or equal to 1/2 an plus an. No, it's the other way around. 6 is bigger than an, so 1/2 an plus 6 is bigger than 1/2 an plus an. That's what's going on here. Okay. Since 6 is bigger than or equal to an for all n, we find 1/2 6 plus an, so an plus 1 is 1/2 6 plus an, is bigger than 1/2 an plus an, which is an. So an plus 1 is bigger than or equal to an, which is what it means to be increasing. Since it's increasing, It's clearly bounded below. By A1, for example. I want to show there's a lower bound. Well, if the terms are getting bigger, then they're all bigger than the first term. That's definitely a lower bound. And is bounded above by 6. It's a monotone bounded sequence, so it has a limit. Ugh. Hooray! We proved that this sequence has a limit. This feels like super overkill, right? Like, why should I have to go through all this? Just take the formula and figure out what the limit is. The slickest way of getting what the limit is, if I wanted to find the limit, the obnoxious thing is that proving the limit tends to require you to know that the limit exists. If an is very close to L for large L, for large N, then an plus 1 is 1/2 an plus L is also about L. And half an plus 6 is also about L. Well, 1/2 L plus 6 must equal L then. Like, if this is close to L when this is close to L, like plugging L in here gives me a statement about L that I can solve for. I get L plus 6 equals 2L. So I get 6 equals L. I can prove the limit exists, but I only proved that assuming that the limit exists. Or I proved that the limit equals 6 if the limit exists. It's a pretty easy computation. To find the limit is 6 if it exists. But we didn't actually know that the limit exists. Like, we needed to do the work of getting the limit to exist before that worked. So this example is a really good example of you need to do the proof by induction to get the limit exists. Once you know it exists, you can find the limit pretty easily. But you kind of have to use these tools to get that the limit does exist. Unless you can find a formula for an, which is not that hard to do. Right. All right, that went a long time, so I'm going to stop talking here. We got through 11.1. How much homework can you do? Do I have that open on a web page? This is my other class. You guys are this class. Let me see the homework list. Yeah, so you should be ready to do 63 through... This is about finding, does the sequence have a limit? This is about showing that the things are increasing. Yeah, those are fun. Yeah, you should be able to get through 85. Where did that start? Oof, this is a lot of problems. Take a look at 63 through 85. Some of these are very tricky. Feel free to ask me about them, and I can talk about them in the next lecture. I might be taking tomorrow off from lecturing. I got some stuff going on, and you got a bunch of homework problems. If I am lecturing tomorrow, I'll send out a text at 3:30 to give you a heads up. But for now, assume I'm skipping tomorrow, and I will see you next time. And yeah, I got grading to do. See ya.